My name is Phil Casini. I'm a Senior Product Manager here in San Jose, and I'm currently responsible for the Cisco ONE controller. Prior to that, I was one of the guys on the strategy team that developed the original strategy for the company. So as you can imagine, that was several years ago. It's sort of blossomed into a number of things. What I was going to cover today was the Cisco ONE controller, but from the perspective of a little bit of a history, where we've been, where we're going, and then talk a little bit about what I think are the two preeminent use cases that at least we see in the circles I've traveled in terms of application of SDN here still in the early days of the evolution of the technology. I recognize some faces in the room here today. Some of this you've probably already seen if you've interacted with me. So I guess my goal today is to sort of level set everybody on where we are in terms of controller development and what we're trying to accomplish with software-defined networking. The first thing I wanted to start with was something called Open Network Environment. By show of hands here in the room, how many people have heard about Open Network Environment? Okay, about half the room. This was an initiative that was announced a little over a year ago at Cisco Live San Diego in June of 2012. And the idea behind it was that when the issue of programmability was beginning to be looked at several years ago at Cisco, we found categories of use cases that had different needs. And so being Cisco, having a broad portfolio of products, we thought that the idea of having programmability in the network would mean different things to different people. And we talked a little bit about that just here today in an implied way with John's presentation, where we talked about onePK and we talked about the idea of programming switches right at the switch level. There's obviously classes of applications where that is desirable. Since then, we've seen a number of applications emerge where the idea of programming the switch is a good thing, but not on a switch-by-switch basis. And so the emergence of the SDN controllers really is surrounding a set of use cases that say, I still want that programmability, but I don't want to have to go switch by switch into my network and have to input that programmability. So I want sort of one pane of glass, I want one moniker that allows me to continue to utilize that kind of a technology, but not have to do that on a switch-by-switch basis. And so the idea of the controller then, in the middle, is the abstraction of some of the control plane functions out of the switches and routers and into largely a software entity that allows you to pull analytics, allows you to connect it to an application, and allows you to push forwarding rules back into the switches. And the controller does that on behalf of either the user or the program. So either you can have a cockpit and a GUI, or you can have a program that automates the policies by which the controller would trigger forwarding rules changes. And you can mix and match them. And that's a lot of what we're going to talk about today, since I'm the controller guy. That's classically what we define today as software-defined networking. That was the vision at Stanford when the original idea of abstracting control planes came about, and it's still in its architecture phase, very relevant today. And what we're seeing is the emergence of production controllers now that will allow you to carry the experimental stage of software-defined networking into a production phase. So we'll talk about that middle box that's in red for the rest of the presentation. The other area that we see is primarily in data centers today, and most of the popularity around virtual overlays comes from the idea of having improved VM mobility. But there are sets of use cases beyond VM mobility that the application of a programmable network makes sense. As you may or may not know, Cisco has had a product in the marketplace for quite some time called the Nexus 1000V, which in effect implements virtual overlays or virtualization in a data center. So the reason I brought this up is that while we're going to talk about the middle layer, I wanted to make sure that everybody knew that there is an initiative here to pull all these things together. And one of the things that I think Cisco will do in terms of adding value to the entire programmability subject will be the ability to have comprehensive virtual and physical management in a mix and match fashion via several projects. The other one is the ability to be able to fold this into a conventional production network. Because as a practical matter, at least I believe that nobody's going to forklift their production network for anything SDN. There are conventional methods that have been deployed that are resilient and scalable today. Why would you change those for any reason? Because they work. So really what we're going to talk about today is we're going to talk about the idea of folding in new kinds of programmability for applications that need it. Okay, any questions? Okay, let's talk a little bit about history and something called slicing. How many people, by a show of hands here in the room, have played with a controller, open source controller, vendor controller? Okay, which one?
Big switch.
Big switch, okay.
Big switch.
Big switch?
Well, floodlight, big switch.
Floodlight, okay. Anybody dealt with the original open source controllers? Knox, Beacon, Maestro, so on and so forth? Okay, so a little bit of history then. 2 years ago, when we basically endeavored to begin development of the controller, the first thing we looked at that time was the landscape of who was using SDN. And there were sort of two camps. It was almost entirely in academia. And one of the camps were the people who were building tools, and another camp was the people who were building applications. And so the tools people were the Stanfords and the Cals, and being here in San Jose, we had local proximity to them. So they were building open source controllers. They were building something called a flow visor, which is a poor man's hypervisor for networking. And the idea was very simple. You could affect network activity and program network forwarding rules in an experimental way in laboratories as needed by the research departments. And in certain cases, you would need to do something a little bit more logical than a VLAN to separate the researchers on the network itself. And so those two components were becoming extremely popular. And so the first thing we did is we looked at those and we said, okay, we understand the tools environment. Then we took a look at the applications. And we looked at a number of universities, some of them in the room here today, with Brent Salisbury at University of Kentucky. Also Indiana University, who was spending a lot of dollars in putting an interoperability center for OpenFlow in place that it now calls InCenter. And then the third one that influenced us was a research center out of the University of Wisconsin in Madison. And we chose those because they commerce about $1 billion a year in research, and they have some extremely challenging high-performance computing challenges in their network today. So just for example, they have 6,000 servers. Their ESNet connection commerces about 1.2 petabytes a day. They get anywhere from 100 to 200 job requests for their HPC a day. That's actually moving to 200 to 400 by the end of this year. So big challenge with networks, big challenge with firewalls, big challenges with load balancing, all of the things that you would conventionally say the early applications of SDN could solve. So what did we find out? We found out that the applications area was using the tools in the experimental colleges, and it was going reasonably well. But the IT departments were facing a challenge, and the challenge is 3 to 5 years from now, looking 2 years behind, these networks were starting to get very sophisticated. And they could grow up to be their own production networks with their own policies. So physical topology aside, it could well be that the security and policy databases would be disparate. And so that was our entry point in terms of where we wanted to go. We wanted to say, hey, in a production network, you don't want distributed policy engines. You don't want distributed security management. And it really doesn't matter from a Cisco perspective whether it's on a campus or any industry that has some combination of a campus and a data center. And so we spent a lot of time incubating the controller development around the idea of taking the SDN capability out of the laboratory and into the production network. And there's a balancing act. You want to preserve, you want to be able to give IT operators the ability to have consistent policy and security database management across the physical network. but you don't want to compromise the flexibility that the researchers in the academic world and the users in the enterprise world would have by leveraging software-defined networking. And so when we looked at the open source tools, we found that there were a number of shortcomings. The first one being in the area of topology management and discovery. And so we spent a lot of time upgrading that. In certain cases, the open source tools created physical connections between the switch and the flow that you would program. In a laboratory environment with 10 or 100 switches or even a couple hundred switches, it's no big deal. If a switch changes, you go in and recharacterize the flow. In a production network where you have to assume that everything changes all the time, that would require an enormous amount of OpEx to support. And so we spent a lot of time looking at how to semantically separate that and create more of a link association. And so you'll hear terms from us like topology independent forwarding, which is the idea that you can create these logical flows, logical links. You can put parameters on how they're used. You can hand them off to the users, and the users themselves will have the freedom within those flows to do what they want, but they are managed consistently and they're logically associated, such that the topology database in the Cisco controller is intelligent enough to reconcile issues when things change in the network. That becomes really important because the second piece that we looked at was the idea of the slicing capability. And when we first looked at this, my own opinion of this was that slicing was going to be a use case for the network. And I'm here to tell you today, slicing is a feature of a network. It is no longer a use case. Why? Because slicing has the ability to logically associate and partition a network without having to go through the management of major VLAN redirection is very appealing from an OpEx perspective. It means you can slice and dice the network on demand, dynamically, and you can change those slices, retire them, add new slices, and because you have flow spec level parameters associated with those slices, you can morph them into sandboxes for various uses, and you can automate all that through policies so that humans don't even have to touch that. That's very appealing. That's kind of the direction that a lot of the laboratory academics were going. The problem is that a conventional flow visor doesn't give you adequate isolation, so that if somebody does something really strange with a slice, it will, 9 times out of 10, unless you have very sophisticated isolation mechanisms in place, it will bring down the network. Now, the academics have gone to certain techniques now to try and prevent that. You'll start to see, if you delve into this stuff, flow visor on flow visor nesting. Something that Internet 2 is pushing right now. You'll see several hop isolation between the traffic that flows through the network, the production network, and these experimental networks. It's all marred in, if you try and just sort of band-aid that, it's going to be a problem in a production network. So we spent a lot of time saying, okay, how can we provide adequate isolation? The answer came empirically for today is we moved this flow visor and slicing activities into the controller itself. So that was a big piece. And then the third piece that we looked at was the idea of how you program these from a programmer's point of view. And we have decided early on in the program that the way in which we should do this is with conventional computer science programming languages with published APIs. And the reason for that is twofold. Number one, in the early days of SDN, it gives people who have to learn how to build these kinds of applications a very common, reasonably well-known starting point. And we chose Java and REST. But the second thing is because we don't know 5 years from now what that interface between that application and that controller is going to look like. I will submit to you today that it's probably not going to look a lot like it looks now. And the reason for that is, as SDN matures, the network state management begins to migrate more and more to that interface between the controller, the northbound the controller, and that application. Application guys who plug yellow cords into a socket and think there's infinite bandwidth with no delay are not equipped to handle network state management on a complex level. And so, depending upon the applications you choose, the network state management over time is going to become an issue. That will all change. And so, I'll talk to you about architecture in a second, but we have a very strong emphasis on making sure everything we do to program this controller is in the public domain and is modular enough so that it can morph over time. So we've picked 2 as a starting point today. I may be in front of you 3 or 5 years from now, and it may be 2 completely different points. Okay?
Phil, one thing
Sure.
on the slicing that I think is where this differentiates itself from VLANs and VRFs is this idea that it's a concept where you can self-provision. So we've never really had mechanisms to self-provision networks. So if you have a large network, you can essentially hand off a slice of that network to either, test dev, a customer. I mean, this stuff really could be monetized. And I think that's a new, definitely a new paradigm.
On the campus too, it's got about low-cost switches.
Sure.
Right, so we could always have done this with MPLS, but MPLS is expensive to implement because you have to have a complex control
Right.
plane, a metric ton of software for MPLS to run, and then you update the flow table with the MPLS entries.
Right.
But if you've got 50,000 Ethernet ports, that's an awful lot of work. And
Well,
so slicing says, I'll just use the flow table to cover it up instead of using MPLS to cover up the flow table. That's all slicing in.
That's a great point. I actually have a use case on MPLS redirection of traffic that I'm going to talk about that I think highlights what you just said.
Well, and even on top of this, you can see a lot of developers developing for things like Amazon. And one of the things, the best practice of Amazon is to use security groups to isolate groups of instances together. And frankly, you have to do that programmatically. So the ability to programmatically segregate groups of instances together and frankly make that very transit available through API is very neat.
And expose an API to a customer. Here's a rack. There's 5 other customers in it. You build your topology however you want.
Yeah,
So-
absolutely.
But how does this, is the idea with the network slicing to say, this department can talk to these server resources and you're isolating it from a security perspective? So then how does,
Everything, not just security. You
okay,
actually want to have one switch at the top of the rack and 20 servers. And inside of those 20 servers is 10 hypervisors. So now you've got 200 servers. You might have 200 separate customers who need 200 separate networks. So
so,
if you could create 200 slices out of that 148 port switch
right,
by isolating the flows
right,
at it, say by MAC address, by IP address, by a combination of both, then you've just created 200 virtual networks.
right. So I guess the point I was getting at was how this compares to like the TrustSec solution, right? Because that seems to me more like an intelligent, you've got something on the back end that's posturing devices,
Sure.
and you have a more intelligent way of
So
saying,
the difference, I think the difference between TrustSec and this kind of thing is this is all about policy enforcement. TrustSec is about policy creation. So, for example, you may see today where TrustSec has SDN built under it so that it leverages a controller for the physical management, but the policy creation is done in that environment. We see that today when I'll talk a little bit about role-based authentication, right? Where does role-based authentication happen? Where does the policies happen that are programmed in the controller? In our demonstrations, we show that through our ISE tool, through AAA, we have radius-based role authentication. A lot of the commercial companies that are looking at this say, why don't you just plug this in my inventory management system, because I got all the policies sitting there, and I know where everything is, and I don't want to repeat that as a separate database, and I don't want to maintain 2 separate databases. So the thing about, I think that if there's one takeaway about SDN controller, is that it's a policy enforcement engine. It's not a policy creation engine. You put the policies in. Now, that could be automated, that could be human. Okay, let's talk a little bit about architecture. One of the comments that was made in the onePK presentation was the provisioning of controllers, where they will be in the grand topology of the network. And for that, and I think there was some discussion about it could be in different places for different reasons, and that is the single biggest reason why our controller is built as a Java VM. So it runs on any Linux server. You can pop it in a data center, you can pop it on the edge, you can pop it in between. I'll show you an application where east-west traffic management at the WAN becomes much more efficient because of the controller. I'll show you in a second the main application I want to talk about today, where you can actually do some very interesting monitoring and analysis of data center traffic using controllers. So you can put it anywhere. And as a matter of fact, as a practical matter, you will have multiple controllers in the system. One controller will not control the entire network. So that's sort of a given in the topology. So let's talk about the role of the controller in terms of the abstractions that were set forth originally by the Slate model. The first one, and we talked a lot about this in the onePK discussion that John had around hybrid switches, and so I'm not going to go and spend much time into that. You know that philosophically, as I said in the beginning of the presentation, that the idea that Cisco has is that you will not forklift production networks. You will roll this in. Rolling this in has two implications. It has implications at the switch, which needs to commingle the traffic that's come from conventional means and traffic that comes from software-defined networking stimulus. The other thing is in the controller. So now we have application layers, and if you take some of the control plane functions out of the switches and putting it into this controller and do all the great things that I said that we can do with ours, you have to connect these up. And so the controller, the way we built it, was built for choice in terms of the southbound interfaces. And we're supporting two today. We're supporting OpenFlow, currently OpenFlow 1.0, and we're committed to the OpenFlow treadmill, and also onePK. So if you saw in things in John's presentation that you thought you liked, but it was a little scary to go program the switches, you can take advantage of the same services through the controller using onePK. And the beauty of that is that now you can mix and match by application what you want to use. If you want to stay more on a standards-based track, you can keep using OpenFlow. In certain use cases, I'll submit to you that the treadmill of OpenFlow compliance and OpenFlow release will not be commensurate with some of the applications and some of the analytics that you need to pull, in particular from the switches themselves. We already see that. So onePK may be a very good avenue for you to implement those applications earlier. But it's about choice. Okay? You have the choice of doing one or the other. As a matter of fact, we wrote the controller so that it's modular enough so that these interfaces look like device drivers, similar to device drivers in an operating system. And why do we do that? Is because, again, 3 to 5 years from now, I'm not going to represent the interfaces you see today are the same interfaces you're going to need. And so in a production controller network, you can't rip and replace. You have to upgrade. Once you deploy this in a production network, you can't start changing vendors on a yearly basis because of southbound interfaces or northbound interfaces. And so our idea is incremental upgrade, and I'll talk about how we do that in a second. The other thing is that the idea of having multiple southbound interfaces addresses use cases as SDN gets deployed to the different topologies. So I heard a little bit about CLI. It would not surprise me if I'm standing up here a year from now and we have a CLI southbound interface for campus. Why? Because it's kind of a neat thing to have a controller and maybe some applications dealing with services provisioning across the campus. And you need some level of CLI to do that, right? In a data center, it's not as needed, but certainly in a campus, it would be very convenient to have. I've already gotten inquiries about modified BGP, ICMP, merging standards out of the IETF. It's all coming and it's all going to be mix and match. And again, the idea of our controller is that we'll accommodate those interfaces as they become popular without having to go forcing them into a rip and replace strategy. The other area that I think is very significant and unique, if you've looked at other controllers, is that we built this controller actually in Java, and we used the OSGI framework. The OSGI framework gave us some value that we thought was extremely important to be consistent with the incremental upgrade strategy that I have proposed. And that is the fact that you can dynamically link modules in real time. So what does that mean to a controller? I've got 40 features in this controller, and you can think of this controller as an amalgam of small Java programs that are linked together in real time rather than one monolithic device. So the incremental upgrade path means that if I have to change something in my forwarding rules manager to deal with a new use case of slicing, I can isolate that engineering upgrade to that piece. To you, that means an incremental upgrade of the controller, not a rip and replace. Okay? The other thing that it gives us is it gives us utility value to extend the controller's capability, either Cisco or you, and write Java applications that can dynamically link into the controller as well. And so an example of that is what we showed when we announced the open network environment. We had partnered with a Hadoop distribution company by the name of MapR. And one of the challenges that they had at that time is in large-scale Hadoop distributions, managing the data replicas. They would go, they'd get set, they'd get thrown into the network, and then they go into this black hole from the cockpit perspective of the Hadoop distribution, because there's no visibility. How do you deal with that? Statically. You go in, you look for them. If you have 2 on a rack, you try and move them. Sometimes you lose them. For small distributions, not a big deal. For large-scale distributions, retail guys looking at point of sale information from 1,000 stores, it's a big deal because it slows down or mutes the efficiency of the distribution. So what we did was we wrote this little Java program called Network Awareness. It was done nothing but allow them to track the locations in the network of the data replicas. Well, lo and behold, their cockpit changed. The REST interface interaction between their cockpit and our controller took about 2 man days to bolt this in, and they had dynamic data replica management capability. And so I offer that because this is the avenue where I think the network operators can add little pieces of code that either they write or they acquire to do very special things for their shop in not only just analytics collection, but also in management of the network itself. The other area that we're supporting is the RESTful interfaces, and that's sort of the most popular one today, gets the most airtime because of the notion of connecting the physical management capabilities of SDN with the virtual management capabilities of things like OpenStack, overlays, and whatever management and orchestration tools you're thinking about. And so we supply those as well. It turns out that the RESTful APIs that we wrote were actually allows you to take the entire functionality of the controller through those interfaces, and we've actually built the GUI as a RESTful interface application on the controller itself. So it gives you the ability to rip and replace the GUI if you like, but I think it's a very good application of how you can use RESTful. And our RESTful interfaces are bidirectional. So, common question. All right, let's talk about a little bit about the use cases that, at least in my sphere of conversations, I think are emerging as the early sort of, this is what you really use SDN for. Up until maybe 4 or 5 months ago, I was probably in the same camp as many of you that said, this is really a neat technology looking for a problem. And I think what's emerging now is small steps to implement SDN in a network. And the small steps are coming from sort of 2 impetuses. The first one is the idea that asking network operators to be hardcore Java programmers isn't a skill set that's widely provided today. The other one is that programming the forwarding rules, while any vendor can stand up behind a podium like this and tell you it's safe, is not going to be something that you're going to do right off the bat. So for those 2 reasons, I think there's, again, a class of application that's coming up that's, I call, rather benign because it solves a specific problem that many people are seeing today. And it's an application of SDN to solve that problem, not necessarily a force fit of SDN to make it work. And so what am I talking about? In data centers today, as they grow, one of the most popular requirements for the network operators is to monitor and analyze more of the traffic, because it's becoming more tied to the business agility of the company, how it operates. And so for quite some time, there's been a solution or a set of solutions that are available from vendors that allow you to monitor and analyze the network. And it goes something like this slide, where you have a production network. You can do optical taps, you can certainly span into a purpose-built high-throughput switch that in effect creates a secondary or an ancillary network that I'll call the matrix network for now. And you can tap this and then connect your garden variety tools, whichever ones are certified for that particular platform, and you're off and running. And if you're doing, I don't know, 50, 100, maybe 200 taps, this is probably a good solution. The problem that we see is that the number of taps are commensurate now with the number of data centers, and you want to be able to coordinate the activity through the data centers from an analysis standpoint. This was the very problem that Cisco IT had when we started going down an application path for this. They wanted to do 3 data centers. They had a number of reasons for doing a large amount of taps, a lot of it driven by video. As you can imagine, we do a lot of IPTV video here at Cisco, and that traffic was causing issues in the network that they needed to have more visibility and control over. And so what we did was we took a look at the problem and said, okay, what are the challenges with the conventional monitor matrix solution as you think about scaling it? And we found 3. We found high cost of conventional matrix switches makes scaling unaffordable. So the reality was for Cisco, the budget to be able to do adequate monitor and analysis provisioning was about 3 to 4 times what their actual budget was. And so when they went back to management and asked for 3 times more budget, how many people in this room, by a show of hands, thought that they got that money? Okay? This is the reality. The other thing that was very interesting is because we have a large mix of video and data in the network itself here at Cisco, the filtering and forwarding capabilities of the conventional switch matrix, primarily statically programmed, was in and of itself a problem. So they wanted something more event-driven because they didn't want to store a bunch of packets on a disk and find out a day later that there's rogue traffic through the network that could have been an attack. And so you either have an amalgam of network operators dedicated to this operation to try and simulate event-driven activities and a large amount of storage, or you try and face the problem of can you create a more dynamic situation rather than a static. Then the tools compatibility itself, and when I went out beyond Cisco IT and started talking to customers about this, I realized that how you actually get information that you actually need out of the system because your network is programmed slightly differently, or the topology is slightly different than the guy down the block, is tool chains. Because you buy these conventional tools and then you have to sort of marry them together, commingle them, congeal them to try and get the analysis and information that you want. And so that seemed very limiting in and of itself as well. And so what we did is we applied the software-defined networking to create our first application for SDN, and it's a new solution that addresses all these 3 challenges. And so the picture that I draw now, which is the SPN approach, which is operational with Cisco IT today, is the idea that you eliminate the matrix network. What you do is you replace it with the purpose-built matrix switches with conventional production switches that you just use to do the monitor and tapping. So it's an extension of the production network applying SDN rather than creating your own a separate network. And that gives you 2 things. We'll talk about that in a second. But the idea here is that now I can also apply software-defined networking in the form of a controller that allows me to do the filtering and forwarding of the traffic on a dynamic policy-based driven basis that can be event-driven because the policies can be sitting in a controller and can be triggered by events. And on top of that, I can connect to the controller itself outside of the matrix network, or in this case, the extension network, by going directly to the controller to provision certain tools that I might build that have very unique characteristics, or at least have trigger points that are very unique to the tool chains that you've already created. And so basically we're replacing the network with, in this case, Nexus 3000 switches, controller and application software. And so with that matrix approach, we've taken the conventional matrix scaling issue off the table by allowing you to provision an incremental upgrade to your production network that is familiar production switches, that also create very disruptive CapEx and OpEx economics that fuels the scaling of the solution. Because again, you're not building an ancillary network, you're basically using lower cost data center switches to replace the functionality. The filtering and forwarding are now event-driven because, as I said, applying SDN enables the controller to drive the policy enforcement in real time and through event-driven activities that can be either human-initiated or programmatically initiated. So I can sit there and write programs and say, controller, go out and monitor traffic in the network, and if that has some view or pattern that I don't like, apply these three filters and give me the solution. And by the way, you may want to have it on a tool on your laptop that pumps it right to your laptop with a big warning sign saying something's going wrong, I think you better take a look at it. Those things are all possible now because of the northbound interfaces, because the connection now are programmatic. And lastly, you can create your own tools. So if you see patterns of traffic that are very unique, you can limit the amount of off-the-shelf tool chains and co-jingling and co-mingling that you need to do. You can write your own Java program. So if you have a rogue pattern in the network, you think it's an attack, you write a Java program, you connect up through the controller so that it filters and flows to that tool, and you're off and running. Okay, application number 2, we talked about monitoring and analysis. Sure, question?
So, I guess I'm a little confused. I thought the last solution you were talking about was a way for me to get rid of having to buy things like gigamons to get spans to all these tools.
Mm-hmm.
So are you implying that with using onePK, I can program certain flows to go to certain IP destinations?
Yes.
Okay.
I'm not implying that. That's exactly what happens. And today, this solution is based on OpenFlow. So you can use the onePK analytics, but today we're using OpenFlow 1.0 is relatively adequate today for that application.
So if I'm spanning things like 10 gig interfaces,
Mm-hmm.
so how are you getting that to the end? I mean, are you doing some kind of like ER span to get it out to the end tool, or is it? I'm just wondering how this is going to work with the actual commercial traffic, right? Because all of a sudden you start spanning. The idea of a tools network for us, right, is that's off net. We
Right.
don't have to worry about aggregation. We don't have to worry about
Right.
access. So if you're using the same switching fabric to get that traffic there, aren't you kind of putting yourself at risk for oversubscription?
No, you're not actually. So it's an intermediate step between the two. You're not using the switches in the production network. You're using production familiar switches to be able to do the tapping. So those switches up top, the SPN matrix, are dedicated to that function.
Oh, gotcha.
Okay, you could do it that way, and yes, there will be issues about oversubscription and resiliency, because now you're not just tapping and mirroring the traffic, you're actually affecting the compute in the switch itself.
Right.
So again, one could imagine we could migrate to that for small networks, but at larger scales, I don't think that works. I think the intermediate step, which is the economic step, is to say, I'm just going to use the same N3Ks I got in my production network. I'm just going to buy a few more of them, stick them in a rack somewhere, and that's my monitoring matrix network. And then I can connect the tools, and I can use the controller to do the filtering and the flows however I want. And it can be span, it can be your span, it could be, I use optical taps here because that's the most common way.
Sure.
So the question now is, I've got monitoring and analysis in my network, and I'm feeling lucky in Google terms, and now I want to take the next step and produce forwarding rules in the production network itself. So let's take that Java application I wrote as an example. I'm doing monitoring, I'm doing analysis. I think it's some rogue traffic. It's not rogue traffic, it's a video conferencing session that's spinning up across my WAN. And it's a telepresence session, and it's a really important high-quality video. I have to make the experience high quality because it's maybe my CEO or CIO or vice provost if you're in a university.
Or your tech field day organizer, for example.
Oh, there you go. And so what is the answer there? You can take that same Java program and extend it. By extending it, meaning you could send an HTTP request to the controller that says, I've been looking at this traffic, I know what it is, and in real time say, it's video traffic. Make sure it goes to wherever it needs to go over my MPLS network. And so here is a diagram of a second application we're going to launch called transit selection, which basically says I have two endpoints, and in this particular case, we proof of concept it around the Cat6Ks, where I have tunnels that I have built that are under SDN control in 3 disparate networks. This was obviously done for university, because for those of you who know, university topologies, they typically have an MPLS network, a public internet, and that internet 2 network as well. But it could be anything. And the idea here is that if I get an HTTP request from my server to the controller that says it's video traffic, I need to traverse it through the MPLS network, the controller will make sure the forwarding rules are programmed on either side to go do that. Same controllers you use for monitor matrix, same servers that you're using for monitor matrix visibility, and the same switches without any incremental engineering. And so this is an application that starts to look at, hey, this is an easy way of me to start to get involved with how I do forwarding rules changes. Does that have implications all over the place for east-west traffic? So, for those of you that have seen or have monitored the ONF, ONS functionality and presentations, there was one about a year ago that Google gave around east-west traffic and how they run their pipes about 95% hot, and everybody, no pun intended, Googled and said, ooh, how can I do that? And part of that answer was, well, so they control all the way to the silicon. This is sort of a way of implementing that kind of thing. And so we're seeing things, for example, with service providers in disaster recovery, where they can slice the network, they can create the tunnels and automate the entire disaster recovery compliance topology and automate the entire thing. And so if you're in a disaster recovery business, you have 100 of things you need to do either a quarter or every month to show that you're actually working. You can automate these kinds of things. In a campus environment, what's happening a lot is YouTube videos going through MPLS and it's congesting the network. And so you can do things like have the controller say, if you classify network as the YouTube videos as secondary, you can move them off into the public internet.
And I assume that in your case example here, these paths were predefined?
Yes.
Okay.
Yeah, you go in and just like, again, you're predefining the forwarding rules.
You just say, move the flow to this path.
Yeah, you're predefining the tunnels in a way that is either on a flow basis or on a slice basis. You have your choice. Okay? And a derivation of that, just sort of to close the conversation around this, is that in the commercial world, for people who have very valuable information that needs to be transacted in a very rapid manner. In other words, the shelf life of the information is sometimes in milliseconds. They can take this transit selection approach and apply a parameter to it. And in this case, we're applying low latency. So what does that mean? If you're familiar with the way financial institutions do banking transactions today, they largely have co-location facilities that are meshed around the world, and most of the equipment is the local proximity of the exchange. Why? Because they want very low latency when they say, go trade this amount of shares. And for the last several years, they've been focusing on switches that are very low latency to help that situation. Well, there's a set of information that triggers the algorithms that have to traverse through the network. That's a given because it comes from multiple sources, and none of the banks generate their own data, nor would they potentially rely on it. And so, as a secondary implementation, we have created a transit selection using the same concept I just described, but allowing the controller to timestamp packets injected in the network and measure latencies of the network itself. And how do we do that? If you're familiar with OpenFlow 1.0, you'll know that there's no timestamping. So we do that through onePK. So here's an example where analytics that are not provided in the standard pipe become valuable for this application. And you all can imagine how the financial institutions look at the difference between 10 milliseconds and 2 milliseconds in terms of triggering the algorithms and what that means to them financially in terms of the revenue they can generate because they can coordinate that traffic. So I can go on and on with parameters. The reason I use this as an example is to let you know that transit selection and the idea of tunneling is a basic concept. Okay, you can apply equal cost, you can apply latency, you can apply bandwidth. I have academic institutions that are looking at this and saying, hey, you know, one of the biggest problems I have is my medical center wants to traverse regulated data through the campus network at certain times. Or, in the case of Madison, I don't want 1.2 petabyte files going through my campus at 2 o'clock in the afternoon when admissions is trying to update the records, or even the bookstore is trying to collect money, which is even a bigger thing for them. And they want to be able to schedule that, and they want to be able to coordinate that using parameters in the network. The scheduling part can happen at the application level, and it can program the controller.
Question, this is reminding me of PFR to some extent, and I'm looking at this slide and realizing that, okay, PFR doesn't match very well.
Right.
Could you contrast them, because I'm also hearing, I think, a policy element.
Oh, in 2 minutes? So everything has its place. I'll submit to you that in general, anything that that I can conceive in SDN, I can conceive through conventional means. The question is what do the economics look like? And particularly, what does the OpEx look like at the end of the day? So yes, the institution that we partnered with to do the original transit selection proof of concept was trying to implement PFR. It was actually trying to implement RSVP. It actually tried to implement several other protocols. Would it get there eventually through conventional means? Yes. We did the proof of concept in 3 weeks by dropping the software into a conventional network with some agents, and it became up and running. So the question is not really a technical question. My answer is not a technical answer, unfortunately. It's one of economics. And that's what I said in the beginning of the presentation, and it's a great straight man to close, which is anything that you'll do in SDN, you can potentially do in a conventional network. The question is what is the OpEx driver? What are the drivers for adopting it, of SDN? There's probably some combination of business agility and OpEx savings. Okay? And if you look at those and say, does the application really need that? If the answer is no, then you're probably going to leave that application to the conventional means. But if the answer is yes, you're probably going to switch to SDN, because that's really where it brings the value.